All right, so we are going to be trying to factor and find the roots of this 15th degree polynomial. It's partially factored into a way in which we can factor everything that hasn't been factored yet. So starting over here, there is nothing to factor with our monomial expression at the beginning of this. This is technically factored already. It just means that there's two copies of x plus 2. This is x squared minus 4, which is a difference of squares, meaning this can be factored further. This would actually break down into x plus 2 and a x minus 2. X plus 4 doesn't factor any further. X squared plus 9 doesn't factor because it's the sum of squares, so we'll leave that alone. X squared plus 7x plus 10 would factor into be x plus 2 and x plus 5. So that is what this one factors to be. And our next expression has a GCF, so this would become x times x squared minus 3x plus 9. Now, I don't know if this polynomial is factorable. I can't think of two numbers that multiply to be 9 but add up to be negative 3, so it's probably not factorable. So let's just rewrite these factors now. So we've picked up an extra 2 copies of x plus 2, so this is going to be y equals negative 3x to the third. That's using the 2x squareds from here as well as the x from over here. We have 4 copies of x plus 2, the 2 of them that are here, the one over here and the one over there. So that's going to be x plus 2 to the 4th power. We have 1x minus 2. We have our x plus 4. We have our x squared plus 9, which we could not factor earlier. We have our x plus 5. And we have our x squared minus 3x plus 9, which couldn't be factored any further. So let's go through and find all the zeros. So what we're going to do is we're going to set each of these equal to 0 and solve. So our first factor, negative 3x to the third equals 0, will only equal 0 when x is equal to 0. All 4 of the factors of x plus 2 will be equal to 0 when x is equal to negative 2. The factor of x minus 2 will be equal to 0 when x is equal to 2. The factor of x plus 4 will be equal to 0 when x is equal to. The factor of x squared plus 9 will be equal to 0 when x squared is equal to negative 9. And x squared is only going to be equal to negative 9 if we take the square root of both sides. We will get x is equal to plus and minus the square root of negative 9. We can factor out the negative 1, which is an I. And the square root of 9 is equal to 3. So at the very least, we have 2 imaginary roots at this point, which makes sense because this is a factor with a degree of 2, therefore it should have 2 solutions. The factor of x plus 5 will be equal to 0 when x is equal to negative 5. And we'll have to solve the last one using the quadratic formula. So we're going to write, I'll write it down here. We have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Just verify what the values are for those. A is 1, so there should be a 1. B is a negative 3. And C is a 9. So if we simplify this as much as we can, we will get x is equal to positive 3, there's a double negative, plus or minus the square root of negative 3 squared is going to be positive 9, because a negative 3 times a negative 3 is going to be 9. We're going to get minus 36 from negative 4 times 1 times 9. All of this is over 2. We get x equals 3 plus or minus negative 27. So the square root of negative 27, all over 2. The largest perfect square factor that goes into negative 27 is going to be a -9, so we're going to keep the 3 here, plus and minus. This will become radical, well, there'll be an I here, a 9, and a 3. All of this is over 2, so we get x equals 3 plus or minus 3i radical 3 over 2. Now, if there was a common factor of 3, 3, and 2, we would be able to simplify. Since there isn't, this is our final pair of roots. So the roots of this problem are at x equals 0, -2, 2, -4, positive 2i, 3i, excuse me, positive 3i, -3i, -5, and 3 plus 3i radical 3 over 2, and 3 minus 3i radical 3 over 2.